Well, this is a recording of a presentation that I originally gave at the SoTiC conference in Trondheim in 2025, and that presentation was about global weakly nonlinear analysis of intrinsic thermoacoustic limit cycles, and I am Philip. So if you follow our work, you know that we perform global linear stability analysis of reactive flows. By this I mean that we take our set of nonlinear governing equations, which are the Navier-Stokes equations, together with species transport equations and closures for reaction rates. We compute a steady fixed point of the set of equations and then linearize them, assuming that we only have small perturbations. And by doing this, we obtain a linear operator, and we can then analyze this linear operator to learn something about the reactive flow. For example, we can compute its eigenvalue spectrum. But having access to the linear operator, we can do much more. So we can look at the adjoint sensitivity of eigenvalues, compute optimal forcing structures using resolvent analysis, or even perform wavemaker analysis. And all these tools strongly rely on our initial assumptions that perturbations were small. However, if we are in a scenario where one of the global modes is linearly unstable, perturbations will grow over time and soon outgrow our assumptions of them being small. So the question arises if we can learn something from the linear stability analysis about the saturated limit cycle where perturbations are of finite amplitude. From hydrodynamic stability theory, we know that the situation is sometimes saved by linearizing about the time-averaged flow fields. So the time-averaged flow fields, also called the mean flow, are different from the fixed point solution of the governing equations, which is also called the base flow. And this difference between mean flow and base flow is the mean distortion. So the idea would be to linearize our equations about the time-averaged flow fields, which are not the fixed point of the governing equations. And the best case scenario we then can hope for is that we find a marginally stable eigenvalue. And the fact that this eigenvalue is marginally stable corresponds to the situation in the saturated limit cycle where the growth and decay of perturbations are balanced. And then we would hope that the frequency of this eigenvalue corresponds to the frequency we obtain from Fourier transformation of our transient signal. One very prominent example where this works well is the wake behind the cylinder, as demonstrated by Berkeley in 2006. So we were curious and wanted to see if we can perform mean flow stability analysis for reactive flows, and we tested this on two two-dimensional laminar premixed flames. One of them is a slit flame anchored on top of a flow contraction, and the other one is a two-dimensional V-flame. In this presentation, I focus only on the slit flame. The V-flame case is documented in the paper. So the flow direction here is from bottom to top, and the flow is at fairly low Reynolds number. We have a Reynolds number of 100. And to keep the derivations in the following as short as possible, we are focusing on we are using a single-step irreversible field-limited reaction mechanism. If we take such a laminar premixed slit flame and put it in an anechoic acoustic environment, it goes unstable, and the mechanism behind it is the intrinsic thermoacoustic feedback loop. In the study, we used this ITA instability to test mean flow stability analysis. And this instability is, while its growth rate is rate controlled by the acoustic impedance that we impose at the outlet of the domain. So this will serve as our bifurcation parameter. And what is very convenient is that the base flow remains unaffected by this bifurcation parameter, because in the steady fixed point solution, we do not have acoustic waves on which the impedance could act. So what happens in this slide is that we modify our acoustic outlet impedance from its critical value, where the intrinsic thermoacoustic mode is just marginally unstable, towards anechoic outlet conditions. And as we do so, we observe for each outlet impedance a saturated limit cycle and Fourier transform the signal, and that gives us here the frequencies over outlet impedance. And we now want to reproduce those results by linearizing the governing equations about the mean flow. But we see that even so close to the bifurcation point, we are not matching the frequencies, and our mean flow is not marginally stable. So mean flow stability analysis is failing for this reactive flow. So for the rest of this presentation, we want to understand why mean flow stability analysis is failing for this simple reactive flow. And to do this, we want to derive an amplitude equation for the limit cycle from first principles. So this amplitude equation is also called the Stuart-Landau equation. It's given down here. And by computing it from first principles, I mean that we do not post-process some data to get the coefficients in this equation, but we directly compute them from the Navier-Stokes equations. And by doing this, we can bridge from linear analysis to the limit cycle, because we can track what terms of the Navier-Stokes equation actually end up in those coefficients in the Landau equation, and that gives us insight into the problem. So at the critical outlet impedance, our intrinsic thermoacoustic mode is marginally stable. And close to those bifurcation points, growth rate associated with this mode are very, very small. And that means that the system develops slowly in the direction of this mode. If we look at the transient data, we indeed find something that has slow time dynamics, and that would be the envelope of the amplitudes of the signal. So what we want to do to obtain the Stuart-Landau equation is perform a weakly nonlinear analysis. And that means that we expand our state vector in a series shown like here, where we have dependence on the fast timescale and the slow timescale tau. And we make the ansatz for the first order perturbations that they go with a slowly and time varying amplitude A, superimposed with fast oscillations. And since the direction of the slow dynamics is the eigenvector associated with this eigenvalue that goes unstable here, we're taking here the shape of the first eigenvector. So what we then have to do is to plug in this ansatz into our governing equations and solve them by order of epsilon. At order epsilon 0, we obtain the equations for the fixed point, so for the base flow. First order of epsilon, we can solve an eigenvalue problem, and at second order of epsilon, we can solve an explicit expression for the mean distortion, which was the difference between the time average flow fields and the base flow, so the fixed point solution, and the first harmonic component of our system response. And finally, at third order, we find the Stuart-Landau equation. So if we look closer at what is happening at third order of epsilon, we find this big linear system to solve. And by looking at it closely, we see that it only has a solution if the amplitude obeys this amplitude equation, which we directly identify as a Stuart-Landau equation. And now the term in front of this cubic term in amplitude is split up in three components, because we want to single out the coefficient that only comes from interaction between the first harmonic and the fundamental tone, parts of the coefficient that are due to interaction between the mean flow distortion and the fundamental tone, and parts of the component that is due to triadic self-interaction of the fundamental tone. And why do we want to do this? Well, if we perform a mean flow stability analysis, we only account for this red box here and neglect the two other boxes. So what we have to do in the following is to check if this assumption is justified or not, and that will answer us the question if mean flow stability analysis would be justified or not for the flow at hand. But first things first, before performing this analysis, we need to verify our coefficients in the Landau equations. So on this slide here in the table, you see the actual numerical values of the coefficients. And first thing to note is that the real part of this B coefficient is for both cases negative, and that means that we have a supercritical Hopf bifurcation. Now we want to verify those coefficients in two limits, and the first limit would be the linear limit of our Stuart-Landau equation. And this we can directly compare against base flow stability analysis for varying impedances. And the second limit we take is the steady limit of the Stuart-Landau equation, and this we can compute against saturated limit cycles from transient time-stepping computations. So looking at the linear limit of the Stuart-Landau equation, we have it here in the dashed black line, and we see that it is tangential in the Hopf point, so at 0, 0 in those plots, to results from base flow stability analysis. And this directly verifies the coefficient A. Looking at the steady limit, we find that amplitudes post-processed from transient simulations become tangential to the prediction of the Landau equations as we approach the Hopf point. And the same is the case for frequencies here. Obtained from Fourier transformation and from the Stuart-Landau equation. So this validates our coefficient B. So with the weakly nonlinear model, we have, of course, access to the base flow, which is a fixed point of our governing equations, but we can also explicitly compute the mean flow distortion. And combining those two fields, we have a model of the time average flow fields, and we can perform a prediction or compute how the growth rate of the time average flow fields should look like and what the frequency should be if we linearize about the time average flow fields. So here on the right hand side we have in green squares the frequency and growth rate from mean flow stability analysis performed on the time average mean fields from transient computations. And we compare that against the weakly nonlinear model, so what we would expect to get. We see that this is a fairly good match. So our weakly nonlinear model is able to explain why mean flow stability analysis is failing. So for example, why we get unstable mean flows. So looking at the split of the Landau coefficient B, we see that only the triadic self-interactions of the fundamental tone have a saturating effect on the limit cycle. And we see that all contributions are of the same order of magnitude. So it's not justified to neglect the triadic self-interaction and the harmonic interaction. And that is also the reason why mean flow stability analysis is failing in this case. So now we want to take the analysis a bit further and look at how we actually compute those Landau coefficients. And we see that they come from a scalar product between the adjoint eigenvector and third order nonlinearities in the governing equations. And what we want to do is to approximate the Landau coefficients by taking only into account third order nonlinearities that come from the reaction rates in the equation. So just from the chemical reaction. And what we see is that this approximation in red well recovers the overall Landau parameter or Landau coefficient. And that means that the Arrhenius law, so the reaction rate closure, is the dominating nonlinearity in the saturated limit cycle. So these scalar products contain integration about over the computational domain. And what we can do is we can look at the density fields inside those integrals. And that tells us from where in the flow contributions to the Landau coefficient come. And we see that the harmonic interaction and the mean distortion interaction, which are both destabilizing in the limit cycle, originate from the flame tip, and the triadic self-interaction, which is saturating or saturates the limit cycle, originates from all over the flame front. So finally, I want to sum up this presentation with the statement that limit cycle saturation is caused by triadic self-interaction of the fundamental tone via heat release and field consumption terms, and this mechanism cannot be captured by global stability analysis of temporally averaged mean field,